we're now going to use the derivative for something. And remember, we said the derivative is simply a rate of change. It doesn't have to be a number plane graph. So here we've got a block of ice, which is a cube. I suppose you could call it an ice cube. Hey? One edge is 10 centimetres long, but it's melting and its dimensions are decreasing at the rate of 1 millimetre per second. They want to know what rate the volume is decreasing when the edge has got to 5 centimetres long. So, all right, we have to work out exactly what it is we're trying to find. There's our cube. I'll call the side of the cube X. We're trying to find how volume changes over time. So we want to find a link between volume and time. Well, I don't really have that. What I do have is a link between the edge of the cube and time. And we know that's, well, it's negative because it's decreasing. And 1 millimetre per second, well, I've changed it into centimetres so it matches the question there. So it'd be minus 1/10 of a centimetre per second. So I have dx to t. I also know the volume of the cube. You see, I've got dx to t, I want dv to t. So ideally now, I want a link between volume and x, which of course comes through the formula, because now I can create dv dx if I differentiate both sides of that. I should be able to put that all together using the chain rule, implicit differentiation, rates of change, whatever you want to call it. It's all the same idea. Because I can now say, hang on, I could get dv to t by getting dv dx and multiplying it by dx to t. And I've worked out both of those things. So I'll give 3x squared times negative 1/10. So I can actually find dv to t without actually having to know what the time is. All I need to know for this formula is the length of the cube. We want when it's 5 centimetres long. So when x equals 5, subbing it in, we get minus 7.5. And then I'll just answer the question. So, okay, well, therefore the volume's decreasing at a rate. Now the rate would be, well, it's volume with respect to time, so centimetres cubed per second. Let's look at another one. A vessel in the form of an inverted cone with a vertical angle of 90 degrees. The depth of the water in the vessel is x centimetres. First thing they want us to do is find the volume of the water. So there's my inverted cone. They told me the angle at the base was 90 degrees, and I've just put a little blue line there to sort of say, oh, well, there's the water line. So the depth of the water is x. Now, we know volume of a cone is, who remembers? Third pi r squared h. Remember, the pyramid is always 1/3 of the corresponding prism. So a cylinder is pi r squared h, so cone would be 1/3 pi r squared h. Okay, I want the radius then. We got h. What's the radius? Well, they've told us that that angle at the bottom is 90. Well, if I chop it in half, I've got an isosceles right angle triangle. So the radius must be the same as the height. So I can work that out now. Volume is 1/3 pi r squared h. Subbing that in, we get 1/3 pi x cubed. So that's the first part of the question. All right, so we're going to pour water in at a constant rate. So we've got our jug of water or whatever it is, and we're just pouring it in at 0.2 centimetres cubed per minute. We want to know how fast or what that rate of the depth is increasing when the water depth gets to 4 centimetres. So we're trying to find dx to t. Now, they've given me a rate. The rate they've given me is dv to t, how volume's changing. It's increasing 0.2, so that's 1/5. So again, if I got dx to t, if I want to get dx to t, I've got dv to t. If I can get a link between v and x, and that was the point of the first question, we've now got a link between v and x, I can create my derivative. Dv dx would be pi x squared. We should be able to link it all together. So dx to t will be dx to v times dv to t. So I turn my dv dx upside down to get the x to v. So 1 on pi x squared times a fifth. So 1 on 5 pi x squared. Okay, we want when x is 4 centimetres. So subbing that in, I just left it as an exact value rather than get a decimal approximation. So the depth is increasing at 1 on 80 pi centimetres per minute. So okay, 7/8, again, just picked a few questions out there to have a look at. And it's actually using our derivative, our rates of change, to solve practical problems. Yeah.